Students, in this video we are going to see what is the force experienced by a conductor when it is placed in an external magnetic field. So imagine you have a conductor of length L and area of cross section capital A placed in a uniform magnetic field B. Okay. So it is a conductor, it will contain n number of charges. So n is the number density of mobile charges. We have studied in current electricity about number density. What is number density? It is the number of charges per unit volume. So we have a conductor of length L, area of cross section A, number density n placed in a magnetic field B. Okay. If n is the number density, then what will be the number density? Means number of charges, mobile charges per unit volume. Then what will be the total number of charge in the conductor? It will be, total number of charge will be N A into L. Okay, I have placed this conductor in an external magnetic field and the charges are drifting with a drift velocity Vd. Now, when charges move in an external field, what happens? It experiences a force, a magnetic Lorentz force, and is given by F is equal to Q into V, here it is Vd cross V. Now, this is for a charge when placed in an external field. So, what will be the total force experienced by a conductor? The total force experienced by a conductor will be N A L Q V D cross B. Okay. Now, we have studied in current electricity the current flowing through a conductor. Equation to find the current flowing through a conductor is given by I is equal to N E A V D. Here instead of E we are taking Q. So, what is the equation for current here? I is equal to N Q A V into D. So, our equation becomes total force experienced by the conductor is equal to, instead of N A Q V D we can write I into L cross B. Or we can write this as F is equal to I L B sin theta, where theta is the angle between the length L and magnetic field B. Next, we are going to see what is the force between two parallel conductors or parallel wires carrying current in the same direction. Imagine I have two wires AB and CD which are placed close to each other and a current I is flowing through the conductor in the same direction. Okay. Now, what happens when I have a conductor? What happens when current flows through a conductor? It will produce a magnetic field around the conductor. Now, this is my conductor AB and this conductor produces a magnetic field around it. My conductor CD. Now, second conductor CD is placed in the magnetic field of the first conductor. So, conductor in an external magnetic field. Now, at this point if I see this is my current direction. So, my magnetic field is like this and at this point it will be going into the board and it is field produced by the first conductor. So, I am going to write it as B1. Okay. Now, a current carrying conductor in a magnetic field. So, it will definitely experience a force which is given by F is equal to I L B sin theta. First, let us see what is the direction of current produced in the conductor. For that you have used the Fleming's left hand rule. Stretch your middle finger, forefinger and your thumb in 3 mutually perpendicular directions, where thumb represents the direction of force, middle finger represents the direction of current, middle finger represents the direction of current and your forefinger represents the direction of your magnetic field. Now if you look into here, you can see my field is going into the board, current is going in the upward direction. So what is my direction of force? This force is towards the conductor AB. So force of second conductor is towards conductor AB. Field, current, force direction. The same way, conductor CD is also having a current passing in the upward direction. So definitely it will also produce a field. So current is flowing in the upward direction. It will also have a field around it. This direction, so field is coming like this, and at this point the field will be coming out. To find the direction of force experienced by my conductor A, what I have to do is I have to use the Fleming's left hand rule. For that, what you have to do, stretch your middle finger, forefinger and thumb in mutually perpendicular direction. In this case, current is going from bottom, from B to C, so upward direction, but my field is towards me. See, my field is coming out of the board. So what is the direction of my force? The force is towards the conductor CD. Hope you understood. So we have, once more I will explain, we have two conductors A, B and C, D. Through A, current is flowing in the upward direction, current I1 is flowing in the upward direction. So it will have a field around it, and the second conductor CD is kept in this field, and the direction of field is into the board. So using Fleming's left hand rule, I find that the direction of force produced is towards AB. Similarly, my second conductor is also having a current flowing through it, so it will also have a field around it, and this field at this point of the conductor is pointing outward. And using Fleming's left hand rule, we find that the force is directed towards the conductor CD. Okay. So the field produced by the first conductor B1 is equal to mu 0 I1 divided by 2 pi r, where r is the distance between the conductors. Now when in this presence of field, we have kept the second conductor, so it will experience a force given by F2 is equal to ILB sin theta. That is the expression to find the force experienced by a conductor in a external magnetic field. Here I is I2 because current force for the second conductor. So I2 into length into field. Now who is producing the field? Our first conductor is producing the field for the second one. So it is B1. Now if you look, current is flowing in this direction. So length is also in this direction. Field is going into the board, which means L and B are perpendicular to each other. So angle between them is 90 degrees. So sin theta becomes 1. So we can write F2 is equal to I2L B1, which can be written as, so B1 we can write mu 0 I1. So I1 by 2 pi r. So the equation becomes F2 is equal to mu 0 I1 I2 L divided by 2 pi r. And the direction of force is towards AB. The same way you can find the expression for the force experienced by the conductor A, B. You will get the same expression. F1 is equal to mu 0 I1 I2 L divided by 2 pi r, and the direction of force will be towards the conductor CD. Okay. And the force expression for force per unit length is F is equal to F2 by L, which is equal to mu 0 I1 I2 divided by 2 pi r. Now, using this expression, we can define what is 1 ampere. Okay. Now, F is equal to mu 0 I1 I2 divided by 2 pi r. F is force per unit length. This F is force per unit length. So, if I1 is equal to I2 is equal to 1 ampere and R is equal to 1 meter, then what is F? F is mu 0 by 2 pi, and which is equal to, we know mu 0 by 4 pi is 10 raised to minus 7. So, mu 0 will be 4 pi into 10 raised to minus 7. On substituting the value, by 2 pi we get answer as 2 into 10 raised to minus 7 Newton per meter. So, 1 ampere is defined as a steady current which flows through two parallel conductors having current in the same direction when placed 1 meter apart, experiences a force of 2 into 10 raised to minus 7 Newton per meter. Okay. So, one thing which we have to remind in our mind is when two conductors are placed parallel to each other and if current is flowing the same direction, the force between them will be towards each other, or we can say the force is attractive. So, two conductors are placed parallel to each other and current flowing the same direction produces a attractive force. Okay. Next, we are going to see what is the force experienced by two parallel conductors, two conductors itself, but current in the opposite direction. The initial case, current for both the conductors were flowing in the same direction, but in this case current is flowing in the opposite direction. So, we have two conductors AB and CD, and for first conductor current is flowing in the upward direction. So, for first conductor current is flowing in the upward direction. So, current is flowing in the upward direction, it will be having a field around it, and at this point the field will be going into the board. So, our aim is to find out what is the direction of current. Here current is flowing in the opposite direction, not like the previous case. So, again we use Fleming's left hand rule. Current is flowing in the opposite direction, but field is into the board. Current is going downward direction, field is going into the board. So, my direction of force is away from CD. My direction of force F2 is away from the conductor. The similar way, conductor CD is also carrying a current in the downward direction like this. So, what happened? It is having a field around it, and at this particular direction, if you take this particular point, you can see the field is going into the board. At this particular direction, the field is coming like this. The field is going into coming like this, and field is going into the board. For this particular point, the field is into the board. Again. So, using Fleming's left hand rule, current is in the upward direction, field is going into the board. Current is going in the upward direction, field is going into the board. Therefore, force is away from the conductor, which means if two conductors are there kept parallel to each other, but if current is in opposite direction, flowing in the opposite direction, then force between will be away from each other, or in a sense we can say the force is repulsive. Now, we are going to find out the magnitude of the force. So, first conductor is passing the current, it produces a field B1 given by the equation mu 0 I1 divided by 2 pi r. Now, so the force produced on the second conductor CD due to the field B1 will be F2 is equal to I2L B1 sin theta, that is sin 90. This I2L B1, we substitute the value of B1, you get mu 0 I1 I2 by 2 pi r into L, and force per unit length is mu 0 I1 I2 divided by 2 pi r. So, whether the current is flowing in the same direction or in opposite direction for the parallel conductors, the magnitude of force is same, but the direction is varying.